may seem that quantum mechanics breaks locality. It doesn't, and we're also going to assume this in our toy hidden variable model, right? That influences can only propagate at the speed of light. So just these three assumptions is all we need to construct our theory. We don't need to see how the model works or anything like that. We just say it works and it obeys these general laws, okay? And the only one that's kind of iffy is this one here, right? We have very good reason to believe the universe is local, or else, you know, you could send signals back in time and kill your grandfather, and logical paradoxes and stuff like that. And this anti-correlation, that's enforced both by the observations of quantum mechanics, right? And by observing when you do the experiment, you always see anti-correlation when you do these experiments. So it's a very safe assumption because you see it happening, right? Okay. So basically, you have some experimental doohickey. What this experimental doohickey, right, does is shoot out periodically particles that are entangled. Okay, so this could be those pions decaying into an electron and positron. It could be a single particle of light getting split into two with opposite polarizations. Anything that you can make be in that entangled state that I wrote on the last board, right? So this doohickey spits out these entangled states. Each tick in time, it spits out a new pair, right? And then we have the option of how we measure on each side. Right, we can, over here we have A, over here we have B, and we can move our spin analyzer, if we're producing spin states, to position 1, position 2, position 3, position 1, position 2, position 3. Now, here's a kind of important point, right? If I measure along the same direction, right, suppose A and B both choose measurement direction 2, well then of course they see their spins be anti-correlated. Okay? And the same if they happen to guess, or rather use, the same measurement direction no matter which direction they choose. If it's the same, then those particles have to be pointing in opposite directions. If they choose different measurement directions, if A chooses 1, but B chooses 2, well then perhaps A gets a spin pointing in this direction, but what's the opposite of that over here? Well, there isn't an opposite, so the answer is actually random. Okay, I'll mention this in a little bit, but this is what we call a mutually unbiased basis. Each one of these directions is a basis for the possible outcomes, aligned with it or anti-aligned with it. So if I measure in one basis over here and another basis over there, well, those results are no longer correlated and affect, and actually, if they have this property that they're perpendicular, we call that mutually unbiased because there's no biasing, you get a random result, and mutually because it's the same in reverse, right? And I'll explain that again a little bit. But the key point here is that I only get this anti-correlated result when I choose both measurement directions to be the same. Okay. All right. So this hidden variable model is constructed in the following way. We define a Wigner symbol named after Eugene Wigner, and it looks like this. I'll move once I'm done writing. Okay. Hold on. Okay. So what does this mean? So the Wigner symbol is a set of instructions for how this experiment is supposed to be realistically behaving. So each of these symbols represents a single run of the experiment when it pops out 2 particles and we do 2 measurements. Okay. The phi's are my measurement directions, right? So we can have phi 1a, phi 2a, phi 3a. So the hidden variable model doesn't know which direction each of these people is going to choose, right? So it has to have a potential result ready for all of them, right? This is the assumption of definiteness. It doesn't matter what we choose to measure, as long as we're making a measurement, there's an answer there waiting for us, okay? We can ask what's called counterfactual questions. In principle, we could just know all of the stuff about the system if we had whatever mechanism we needed to look inside of it, right? So this is saying that no matter which outcome, or rather which measurement I make, the outcomes are all predefined. So if I measure A along direction 1, I get a result. If I measure A along direction 2, I get a result. And if I measure direction 3 from A, I get a result, right? And the same for B. So this is, in case you can't read, phi 1A, phi 2A, phi 3A, then phi 1B, phi 2B, phi 3B. So all the possibilities of each run of the experiment. So an example of a Wigner symbol would be plus, plus, minus, 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 plus. And this just means for this particular run of that experiment, if A measures direction 1, she gets aligned. And if Bob measures also direction 1, he gets anti-aligned. They're anti-correlated. Okay? If Alice measures direction 2 and Bob measures direction 2, they get, again, anti-correlated. Same if they both measure direction 3, right? All of these symbols are written in such a way that they're anti-correlated in the same measurement position for that symbol. Okay. So if Alice and Bob measure different directions, well, then they just get different results that are not anti-correlated. So if Alice measures 1 and Bob measures 3, well, then in this case, they both get aligned. So a hidden variable model, then, regardless of how else it works, like what the little bits of it are, right, the actual mechanics of the theory, the results can be thought of as just being a list of these symbols, right? You imagine that the particle has just like a little tape, and it reads off the tape this symbol, and then the next symbol, and then the next symbol, and then the next symbol, and it just runs mechanistically through those results, however they may have been attained. Okay? So we can also assign numbers to the Wigner symbols according to how often they appear on this, imaginary list, how often they happen. How often do those results occur when we make those measurements? So that then would be at the level where quantum mechanics is, right? Quantum mechanics only gives us probabilities, but if we count up how frequently various outcomes occur, then that's the theory, right? Those probabilities that we compare to quantum mechanics. So we assign now a number between 0 and 1 to each Wigner symbol depending on how often it appears on the list, right? If it was 0, it means that particular symbol never appeared on the list. That result never occurred when we performed an experiment. And if the answer was 1, well, the hidden variable model would just do that same thing over and over and over and over again, right? Because that symbol was always there, has probability 1 of being there. Okay, so what if we want to find a possibility of getting both spins aligned with the measuring apparatus, both spins giving a positive result when we measure different directions, right? 1 versus 2 and 2 versus 3 and 3 versus 1 also. Well, we can find mathematical results for this if we know the probabilities are Wigner symbols. Well, even if we don't, we know that those probabilities are just going to be the symbols that allow that result to take place added up. So this is the probability that if we measure along direction 1 and along direction 3, we get both positive results, 2 alignments with the measurement apparatus. Well, we just add up all the symbols that allow for that to happen, all the ones that have a plus here and a plus here. And it's only these two symbols, right? And the reason that there are so few Wigner symbols is because of this requirement of anti-correlation, right? Of course, I could fill out a symbol that was all minuses or all plus, but those don't obey the anti-correlation that this system has, right? So only these two symbols add up to give us the probability of Alice measuring direction 1, Bob measuring direction 3, and then both getting positive results. So P12 would then be plus minus minus, minus plus plus, and then plus plus minus plus, minus plus minus. And then if we did the same thing for P23, we would get plus plus minus, minus minus plus, plus minus plus minus, plus minus plus. And note that, wrinkle my notes, this symbol here, oh, it's almost gone. Do I have another blue? I think I do have another blue. Right. I could have been using blue this whole time. Well, live and learn. Hopefully this one last good marker keeps me to the end of the semester. Okay, so this symbol is the same as this symbol. And this symbol is the same as this symbol. So, what I'm going to do next, now that you've noted that there's these two symbols in both these expressions each, I'm just going to write down a mathematically true statement, right? All of these symbols must be between 0 and 1. So if I write, this will take me a second, hold on. Okay, so I've just written a true mathematical statement, right? If all of these Wigner symbols are numbers between 0 and 1, well then I've got this one here plus this one here. So then these two guys are the same as this guy and that guy, right? So that's the one I underlined in red before. And then this guy is the same as this guy, so that's the one I underlined in blue before. So on the left hand or upper side of this inequality, I have two symbols. And then on the right or lower side of this inequality, I have those same two symbols plus another 2. And if all of these have to be between 0 and 1, it just must be the case that this side is greater than or equal to this side. Okay? But then these are all the probabilities I had just written down here, right? This one here, right, this is P13, and then this one here, this symbol, and then this one, that's P12, and then this symbol, and then this one, that's P23. So, the grand result is that P13 must be less than or equal to P23 plus P12. So this is the Wigner inequality. Now think of how powerful a statement this is. We started with nothing other than three very fundamental assumptions about how this model must behave, and we found an inequality that bounds the measurement results of this system without even talking in detail about what that system actually is, right? It just tells us that the measurement results, as defined by our measurements, right, along those three orthogonal directions, have to obey this inequality. Well, what we can do next is construct an experiment that actually does this. And one way we can do that is by producing photons that are oppositely polarized, right? And look at entangled states of that, and do this experiment. Well, we'll find, we're not going to do it, but you can find measurement directions, A, B, and C, that satisfy this Wigner inequality, that give you results that break this inequality. So if we do that experiment, right, we shoot out photons, we pick a few particular measurement angles, and we analyze the results that we get are 3/4 less than or equal to 1/4 plus 1/4. So the theoretical predictions and experimental results of quantum mechanics can go beyond this inequality, can break it, right? I don't have to have P13 bounded by P23 plus P12 anymore. Quantum mechanics is more general. So this experiment in a dozen different flavors has been done probably 100 if not hundreds of times. Every time more accurate and closing more loopholes and doing all this other stuff, and the results of quantum mechanics are always shown to be correct. So we have to abandon that hidden variable model, right? We started with three assumptions, and we really believe that locality is true, and we really believe anti-correlation is true. So the assumption that we have to throw away is that idea of realism or definiteness. That means that essentially that long list of all the weird things about quantum mechanics must be true, right? People still construct hidden variable models and do research into them, but they don't have one or more of those assumptions built into them. So interpretations of quantum theory, and this is something we can talk about more, have to agree with the results of experiments, right? Even though they may seem counterintuitive. So if you want to have an interpretation of quantum mechanics that's deterministic, that says that the world operates like a clock without probabilities, that Einstein's famous God does not play dice with the universe. If you want to believe that, you end up having to believe something else that's potentially weirder. Like you might have to believe that, well, locality is not true. Influences can travel faster than the speed of light. Why don't we have time travelers showing up all the time? Well, maybe we do. Who knows? It's that level of like, well, if you reject quantum mechanics, Bell's theorem tells us that, well, you'd have to accept something else that's weird, essentially. Many worlds or various other types of interpretations. Okay. So essentially we're stuck with quantum weirdness, right? So now the next question might be, okay, if this is the way reality works, can we use this to our advantage somehow? Can we make some kind of interesting technology with this? And of course, along that same vein, how can we learn more about these types of systems and understand in more detail about how they behave? Okay, so what I'm going to talk about fairly briefly is the idea of quantum cryptography. How you can send secret messages and be guaranteed that no one is listening in. Guaranteed by the laws of physics themselves. Okay, so suppose we just want to send a regular encrypted message like we would now. Well, if we want to send a secret message, here's the best way to do it. Start off with some message. So let's say that this is the message 010011110, Right? This is information that Alice has. Alice wants to send this information to Bob. And she wants to do it over a channel that she cannot trust. Right? Maybe people are eavesdropping or something else. So what she can do is add her message, modulo 2, with random noise. No, that's not the right part. 01101. Okay. So if she has a bit of random noise, she can add that modulo 2 to her message and get a new message. So adding modulo 2 just means it's like adding on a loop, right? Two-step loop, right? 0 and 0 give you 0, 0 and 1 give you 1, 1 and 1 give you 0 again. Okay. So that gives Alice 0, 1, 1, 0, 0, 0, 1, 1. Now she sends this message over some untrusted channel to Bob, who gets 0, 1, 1, 0, 0, 0, 1, 1. He adds that modulo 2 with that same string of random numbers. 0, 1, oh, no, 0, 0, 1, 0, 1, 1, 0, 1. And he recovers the message that Alice wanted to send him. All right? 0, 1, 0, 0, 1, 1, 1. Okay. So it's been proven that if you encrypt messages in this way, there is no way for anyone to decrypt that message because it's been mixed with random noise. Okay, so that message looks like noise to anyone who has no part of this secret key. Okay, if you use this string of numbers more than once, or if your enemy, your eavesdropper, your adversary ever finds out any of it, then they can, in principle, break your encryption and find out the message. Right? So this is what's called one-time pad cryptography, because you would have a pad, right, with strings of random numbers, and then you would use each one once and then never use it again. The problem with this is that both Alice and Bob have to have prearranged these strings of random numbers, right? And if they don't have that, then they can't use this protocol, right? Or if anyone else has gotten a peek at those secret numbers, they can't use this protocol either. So though it works perfectly with a very large caveat of you must create and distribute these random numbers to all parties who you want to receive your secret message, which is difficult at minimum. Okay. So now I'm going to talk about how we can do a quantum version of this that allows us to transmit this key itself, right, and be sure that no one else has looked at the key. And before I start talking about that again, or before I describe the protocol, rather, I want to talk about that mutually unbiased basis thing again, right? So mutually unbiased basis, that if I have a basis, I'll draw a basis like this, right? If I have some basis, say up, down, and I produce states, right? One flies, up flies out this way, and down flies out that way, right? If I have a basis like up, down, and I produce these correlated states, if I'm looking at another basis, say left, right, this up, down, these up, down results are random in this left, right basis, right? No matter which one of these I look at in the wrong basis, I get a random noise, okay? They will still be anti-correlated, right? So if I shoot out a left and right, or excuse me, an up-down pair, right, and I measure on each side in the left-right basis, I'll still get, right, anti-correlated spins, but I get random anti-correlated spins, okay? Whereas if I shot out a right this way and a left this way, I would get just still random anti-correlated noise over here. Okay. So that's a mutually unbiased basis. So how does the quantum cryptography protocol work? So the one I'm going to describe is kind of the simplest one. It's called BB84, in case you want to read more about it. There are more advanced protocols now. Do I need to? Yeah, I'm going to erase this. Okay. So I've got Alice over here. You know what, I got a lot to draw, so I'm gonna just pause and then draw it. How about that? Okay, we're back. Okay, so here's how the quantum key distribution protocol works. Alice chooses a basis, either up, down, or left, right, and she produces entangled pairs in this basis. So this first run, she produces an entangled pair. She measures one of them, gets, in this case, a down result, and then she sends the other one to Bob. Okay, she does this many, many, many times. So she produces it, she chooses randomly, up, down, left, right, up, down, left, right, shoots one particle, probably a photon, over to Bob, measures one herself, and then she gets a series of results, right, depending on what basis she chooses. She measures in the same basis that she chooses. She knows the basis that she produced it. So she gets down, up, left, down, right, let's say. Okay. So those the other half of the entangled pair, whether they be a photon or something else, gets sent over to Bob. Now there is Eve, the nefarious eavesdropper, who maybe can grab some of these particles out of the stream, right, out of the fiber optic cable or whatever it happens to be as they're going along. She wants to siphon off a few of these particles and use them to try and figure out what kind of key, right, these guys are trying to create. Okay, so Bob then guesses the measurement basis randomly. He doesn't know what basis Eve created it, right? She keeps that information to herself for now. Okay. Bob guesses up, down, left, right, left, right, left, right, up, down. And he gets measurements that are along one of those two directions in that basis. So let's look at this first one. Alice produces an up, down. She measures, she gets a down. Bob randomly chose the same basis. There's only two options. And he gets the anti-correlated result. He gets an opposite result. Now later, if Alice and Bob decide that their secret key is safe, then they could use this as one of the bits of that correlated random noise to send a one-time pad message. So this is about, again, creating that secret key remotely between two people, okay? Or a person in an alien or a dolphin or machine intelligence. I don't want to be prejudiced against non-persons or non-humans. Or was I? So next time, Alice produces in the up-down, right? She measures an up. She sends a result to Bob, but this time Bob, by chance, picked the wrong basis. He picked left-right, and so he gets a random result. He gets right. Okay. And then what happens next? Well, now Alice produces in left-right. She gets a left, and she sends this particle. But this is one of the ones that Eve decides to snatch away and read to try and figure out what they're up to. Okay. So she intercepts this particle and happens to guess the wrong basis. She happens to guess the up-down basis, even though this was produced in left-right. And because she chose the wrong basis, she gets a random result. Let's say she gets a down. Okay. Now, Eve doesn't want Alice or Bob to know that she's there, because if they find out she's there, one, they'll probably try and kill her. I mean, they're spies, they do things like that. And two, is that if she reveals her presence, well, then Alice and Bob are just not going to exchange their secret message, right? They're just exchanging the key right now, right? So if they find out while they're exchanging the key that someone is listening, they're just not going to send that secret message. And Eve will never learn anything useful, okay? So she has to disguise her presence by retransmitting what she measures down in that same communication line so that Bob doesn't see any missing particles, right? So she measures, she gets a random result, and she resends that random result. Bob, let's say, now measures in the opposite basis of Eve. Let's say he measures in left-right, and because he's measuring in a basis that Eve is not producing in, he also gets a random result. He gets left. Okay. So Alice and Bob do this many, many, many times. Eve intercepts some percentage of those particles and measures and resends as best she can. And then when that's done, Alice and Bob go to compare their notes. Right? Alice says, okay, I produced in up down and I got it down. Bob says, well, I measured in up down and I got it up. Okay. Now this would be you wouldn't use this part of the key for transmitting your secret information later because you've announced the results, right? But you do this to some percentage of all the, right? This isn't just like you wouldn't do this 5 times, you would do this millions and millions of times and take some percentage, right? So if they don't detect any eavesdropper, they'll use some other bits that they haven't announced the measurements of, or rather the results of, to transmit their key. Okay. So next run, right? They're comparing. Alice says, okay, I produced in up down.